Hi everyone, welcome to the November webinar for the 2BCC. Today our speaker is Dr. Joon Lee from the University of Tennessee, Knoxville. And Junsu, we have a full room here for you and you are good to get started whenever you're ready. If anyone has any questions, please just hold them till the end. Thanks.
Well, thank you very much for the introduction. When anyone can ask questions in the middle, I'm fine with that. And it's my great pleasure to give a seminar today at 2DCC. I'm going to talk about superconductor-semiconductor hybrid systems for quantum devices today. This is not about 2D materials, but I will talk about 1D systems and 2D systems in semiconductors or superconductors. And also I'll talk about materials and how to improve the materials. So it'll be interest for the 2DCC. So I will give brief introduction about superconductors and semiconductors and hybrid systems of these two systems. But as everyone may know, superconductivity is phenomenon of losing resistivity when you cool down the material. And the Cooper pair is formed. It's a pair of electrons when you have the temperature below Tc. And the condensation of Cooper pairs will be happening at the band gap. And semiconductor materials with electric conduction between conductor and insulator. So if for the conductor, you will have overlap of the conduction band and valence band, so you have electrons everywhere. And insulator, you have a large band gap. But semiconductors have medium, the moderately sized band gap. So you can either have insulating behavior or some conduction when you have when you change the Fermi level or the doping. And semiconductors have been used a lot for the computers and other electronic devices. So like 1947, we have a very large transistor, but after like many years, now we have more than 10 billion transistors in a smartphone or PC. And there are many applications of semiconductors like electronic devices or like solar cells, photonics, and sensors. And these days, the semiconductor is also used for quantum computing. So people use that for spin charge quantum computing or topological quantum computing. And my focus is more on the topological quantum computing. Topological quantum computing is using some quasi-particles named non-abelian anyons, and these can be braided, and then these can be used for storing or generating information in quantum computing. And Majorana fermions are promising candidates for that, for the topological quantum computing. And now I want to talk about superconductor semiconductor hybrid system. So the question is, what happens if you interface a superconductor and a semiconductor? So superconductor has Cooper pairs in it, and also you will have a gap, superconducting gap. And when you introduce a normal metal like semiconductor, then what happens? At the interface, maybe you will have some Cooper pairs going into the semiconductor or normal conductor. And and this proximity effect is stronger when you have very clean interface. And when you have electron going into the superconductor, then it will form a Cooper pair, and then you will have a hole reflected from the interface. This is called undrafted reflection. And what about you have one more superconductor? Then you will also have leaking of Cooper pairs from the other side of the junction. So in the middle, you will have Cooper pairs from the right-hand side and left-hand side. And if the thickness of the semiconductor is thin enough, then these can be overlapped, and you will have superconductor or Cooper pairs in the junction. So this can be give you spark currents, and also this induced superconductivity can be used for many applications or studies of physics. And also, when you have two superconductors and a semiconductor, then you will have multiple undirect reflection going back and forth. So that's what is going on when you have a junction like this. And the phenomena based on these proximity effect is containing spark current. So if you have two superconductors and an indium-antimonide semiconductor, then if the junction is small enough, then you will have Cooper pairs everywhere, and you will see the spark current. And if you apply magnetic field across the junction, then you may see the Fraunhofer interference. And also by applying some photons, then you can get Schachter steps. But these can be seen in a superconductor, semiconductor, superconductor junctions. And also these days, this material system is interesting for quantum computing applications. So semiconductor superconductor system can be used for gate-mode qubits. This is an example. And also, this system can be used for topological quantum computing using Majorana bound states. And my focus is more on this Majorana bound states. So this has been proposed by Kitaev in 2001. So you have a 1D system. And at the end of the 1D system, you may have interesting quasi-particle system, quasi-particles. And so he suggested two different modes. One is trivial mode, non-topological phase. Then these Majorana fermions are they are bound together, and there's nothing remaining things at the end. But if you have topological phase, then these two particles can be connected across the sites, and at the end you will have unpaired Majorana fermions. But these two are the unpaired fermions. And this can be used for interesting things. And end states can have zero energy state. So this is the superconducting gap, and in the middle, you may have zero energy states, and that can be measured. But people try to measure that to evidence the Majorana fermions. And superconductor semiconductor nanowires can reproduce this toy model by Kitaev. So you have a semiconductor 1D wire, and then if you interface a superconductor and apply magnetic field, then at the end of the nanowire system, you may see the Majorana bound states. So these are needed. So it should be 1D system, like proposed by Kitaev. And then the semiconductor nanowire should have strong spin orbit coupling. So people use indium antimonide or indium arsenide, because those materials have strong spin orbit coupling. And you need to apply electric field or magnetic field to tune the band structure, and you need to interface the S-wave superconductor. So let's talk about strong spin orbit coupling and the material for the semiconductor. This is a periodic table for 3-5 semiconductors. So you can have gallium, indium for group 3, and arsenic, antimony, or bismuth. These are group 5. So you can form gallium arsenide, gallium antimonide, or indium arsenide, indium antimonide. But indium is heavier than gallium, and antimony is heavier than arsenic. So if you go to heavier materials, you may have stronger spin orbit coupling. And if you look at this right-hand side, it is showing the band gap of these gallium arsenide, indium antimonide materials. And as you can see, indium antimonide is heavier than the other materials. So as you go this direction, the band gap size becomes smaller, and you may have a stronger spin orbit coupling. But people have used indium arsenide and indium antimonide much for the study of these topological superconductivity systems. And there are many other semiconductors, but I'm going to focus more on these two materials today. Okay, so for the first part, I will talk about how to prepare good junctions. So superconductors can be deposited using epitaxy and shadowing. I will talk about that. And then semiconductor systems can be many different kinds. I'll talk about 1D nanowires and 2D electron gases and selective area growth nanowire. And also in the middle, I will talk about some devices like SNS junctions, superconducting islands, and Majorana devices. And in part 2, I will talk a little about control of the tin phases. The first one is 1D nanowires, and I will talk about how to do epitaxy superconductor using shadowing schemes. So this is experiment, first smoking gun experiment of Majorana zero modes. This is from Delft, and the wire was from Eindhoven. And if you see here, this is the indium antimonide nanowire, and superconductor was deposited by e-beam evaporation or sputter, and it's not nitride. And this is normal metal, like gold. And if you apply magnetic field along the direction of the nanowire, then interestingly, in the middle of the this is voltage versus the IDV, and at the zero voltage, there has been a small peak, which may indicate the zero energy state. So what is going on here is the device here is like a nanowire with superconductor, which is nitride, and then you can gate the nanowire part to tune the chemical potential, and then you can have tunneling gates to do the tunneling spectroscopy. So by changing the bias of the normal metal, you can tunnel into the superconducting regime. You can go into the superconducting gap, and by going into the zero energy state, you may see the zero energy. By going into the zero voltage, you may see the zero energy state, and that is the signature here. And if you look at the size of the peak, actually it's not very large. The theory says it should be 2 squared over h, but this peak is like 0.1 of the theory value. So it was not very prominent peak, but it like 10 years ago, it was very interesting results, and it was published in Science. And then because of the peak, the zero-bias conductance peak is not very large, people try to improve the materials and devices. So this is what happened in 2012. So what happened was argon annealing was used to remove the native oxide of indium antimonide, and then argon nitride was deposited. So the interface between the superconductor and semiconductor was not clean. And after a few years, to make the interface clean, chemical removal of oxide was used. And it was by the sulfur passivation. And then right after removing the oxide, people moved the nanowire sample into a sputter in a minute or so. So now the surface is better, and the result was better than the first experiment, but still the peak size is not like the theory value. And then another improvement was made by using epitaxy aluminum. So now the nanowire was placed in a ultra high vacuum chamber, like an MB chamber, and atomic hydrogen was used to remove the native oxide. And then in situ aluminum was deposited on top of that. So this is a TM of the nanowire with aluminum. You can see indium antimonide nanowire, and then aluminum was grown on top, and the top is aluminum oxide, because we take the sample out of the chamber, so you will have the aluminum oxide. And then devices were made, and this is the same kind of data, but as you can see, the zero bias conductance peak is much higher than these ones. But you need to be careful about this paper because it has been retracted, and then this may not be the quantization of that, but the point here is you can improve the signal by having better materials.
So Junsu, Nitin,
Yes.
can you just comment for the audience a little bit more in terms of why was the paper retracted? In other words, the data are real, right? I mean, this is measured data. It's not that the data was fake or anything like that. But
Right.
why, just so the audience gets an understanding, what was the nature of the retraction?
Yeah, I will talk about it in a few slides.
Okay,
So
okay.
So this is by epitaxy. Epitaxy is like growing up another layer on a substrate, and MBE, molecular magnetic epitaxy, was used for this aluminum layer. But there is another issue remaining, because when you make a junction, you need to remove the aluminum layer, for the junction, right? And then aluminum removing is by fabrication, and that can give you another disorder to the system. So to avoid that disorder by fabrication, we also use the shadowing scheme to make better junctions. So this is the indium nanowires, and they are facing to each other. And if you have a control of aluminum flux direction, then you can shadow aluminum on each nanowires. So if you look at here, because of this a wire in front of the other one, you can have a shadow junction. So this is the junction of that part. This is indium nanowire, and aluminum is grown like this. So in the middle, you got a junction which is very clean. So using this epitaxial aluminum scheme and then shadowing scheme, I can make a good junction, and that can give you a good improved signal. But as Nitin mentioned, this paper has been retracted, but the data is real. The main reason for this is, as you can see from here, from the notes, the calibration, there has been a calibration issue. So some people raised questions about the data, and then the Delft people checked their data again, and they found some calibration issue, which is like 8% off. So they think this may not be the real quantization. And also there has been a little selection of data, and that has been also people also raised about that. And then, but that from this note, that was not the main issue. The main issue was the calibration issue. People were not sure about the real quantization of the data, so it was retracted. And the second retraction was from the paper I talked about, the shadowing scheme. But the material and the scheme is not the issue. The issue was from the transport. From the transport data, there was some kind of cropping of the data. So by showing this is just a part of the data, but if you look at the other large area, the claim of elastic transport was not supported. So that's why the paper was retracted. And then, as you may know, there was another retraction of the Majorana fermions or Majorana bond states. And this material system is chromium doped bismuth antimony telluride. And also this people have questions about this data, and then it was finally retracted. And this is a different kind of experiment. So you have nanowire, indium nanowire, and aluminum was covering the everywhere. And in this paper, they claim that the signal here in the middle of the voltage bias is maybe the signature of the Majorana bond states, but yeah, this was not retracted, but people, there was a concern of the editorial board. So this field is rough. So it's not easy to get high-profile papers, and then people have many questions about their data. But there's a consensus that we need better materials. So if you look at this paper, the disorder-induced zero-bias peaks can mimic the Majorana fermions. So if you have some disorder in the system, you may see some interesting data like the zero bias conductance peak, but that may not be from the real Majorana fermions. And also this paper from Shankar Sarma, it pointed out the progress needs to be made in materials. So that's why, and that's the motivation of my study. I want to improve the materials. Then the question is, what can you do? What can you improve? And if you look at this plot, you may have some hints of what to do. So this is mobility of the semiconductor material, and the y-axis is topological superconducting gap. And this is from indium arsenide, indium antimonide. So if you look at these two parts, indium antimonide has larger topological gap. That means if you have stronger spin-orbit coupling, then you may have a larger topological gap. Also, only from one curve of indium arsenide, if you improve the mobility of the system, then you can have a larger topological gap. So that's another thing. And from indium arsenide, there are two lines. One is aluminum, the other is higher TC superconductor. So that means if you have higher TC than aluminum, then you can improve the topological gap. So there are three ways of improving the materials. One is making the mobility higher. The second is having stronger spin-orbit coupled materials. And third one is have the TC higher. And let me talk about the higher TC superconductors. So you can choose many superconductors. And mostly people have used aluminum. And aluminum has 1.18 Kelvin bulk TC. And actually that's not very high. You need to use helium-3 to reach to that interesting features, right? So people have studied more, like if you look at these like indium and tin, lead, mercury, and vanadium, and so on. But you want to choose, for example, if you look at niobium, it has higher TC, like 9.25 Kelvin. But you want to choose type 1 superconductor rather than type 2, because type 2 superconductors have some vortices when you apply magnetic field, and they can induce some subject states. So you may not see a clean data if you use type 2 superconductors. So the red circles are type 1 superconductors, and you can see aluminum, indium, tin, lead. So these have higher TC than aluminum, and also tantalum. So that's why we have tried to use these materials to make the similar devices we have studied. So this is tin. So we use tin instead of aluminum. And this is grown on indium antimonide. So everything is same. We use the shadowing scheme and epitaxial tin on top of indium antimonide after hydrogen cleaning. So we achieved nice clean interface between indium antimonide and tin. And this is junction made by the shadowing. And tin has higher TC than aluminum. So it has been like, it has TC of like 4 Kelvin, and aluminum has 1.5 Kelvin. And from the devices, we also saw hard superconducting gap, which has been seen also from the aluminum devices. And the superconductivity can be seen up to 4 Tesla. For aluminum, nearly 2 Tesla is the maximum magnetic field. And tree charging was studied. So this is a tin island in the middle of two tunnel junctions. So when you give electron into the tin island, let's say this is a superconducting island, then the superconductor should form a Cooper pair. So you need to give two electrons into the island. And this data is showing the tree charging. So here, when the field is small, then you need to give, we are changing the gate. This is backgating. You change the gate, and that is showing you jumps of two electrons. So this is the tree charging signal, and this is 1A charging when you give when you apply higher magnetic field. But you may think that this is for sure, right? You need to have two electrons for a couple pair, so you should see two charging in a superconducting island, but it has not been seen in many materials. Aluminum has been seen. I mean, two charging has been seen in aluminum, but actually, other than aluminum, this has not been seen. So you need to have very clean system, clean material system to see the pre-charging. And actually, tin was the second material to show the pre-charging. So this was that's why this has high impact, and it was published in Science. So now I show that the shadowing scheme and epitaxial superconductor deposition scheme can be used in nanowires. This is great. So initially, people didn't use the superconducting aluminum, and epitaxial aluminum was used, and now shadowing is used to make the better devices. Okay, and I want to move on to the next part of to the electron gases. And the reason for using 2D electron gases and selective air growth nanowires is for scalability. Because then one thing, nanowire is good for making like single devices, but in the future, if you want to make a scalable topological quantum computer, you want to make some scalable scheme to have the semiconductor networks. So 2D electron gas can be used. You can just grow the 2D material, and then you can fabricate later on to make the networks. And this is showing the electron mobility in y-axis and a G-factor. And as I mentioned earlier, indium arsenide and indium antimonide has higher G-factor than gallium arsenide, and also indium arsenide antimony can have even bigger spin-up coupling. But here the point is, these are data from the 2D electron gases, and this one is from the single nanowire. So by having 2D electron gases, you can have higher mobility, which is good for getting higher, larger topological gap. So this is an advantage of using 2D materials. And on top of a 2D, if you have a shallow the top barrier, then if you just deposit clean aluminum on top of it, then aluminum can couple with indium arsenide 2D. This is because the top barrier is very thin. So this is the electron wave function of the 2D, and that if the top barrier is thick, it should go to 0. But because it's very thin, it doesn't go 0. So you can have some coupling at the surface, and you have aluminum next to the 2D. So that's why you can use very thin near surface indium arsenide 2D for superconductor semiconductor systems. So you can form SNS junctions using this material system and see some supercurrent and other interesting superconducting, induced superconductivity features. And also you can form this kind of nanowire shape aluminum layer, and then top gating from the global top gating. You can form some kind of, effectively a nanowire of the aluminum and 2D system. And using this material system, people have seen zero bias conductance by applying some magnetic field along the direction of the aluminum nanowire. And this study is from the Microsoft team, and they use a 2D and aluminum system to form these devices. So basically, this is aluminum nanowire in the middle, and these yellow ones are just gating. So you can tune the chemical potential of the middle part, and then can carefully measure the Majorana bound states. The spectroscopy of the end states, and they did a very careful study of changing field and gate voltages. So they found good areas that may be from the Majorana modes. And 2D, not like the nanowires, 2D is a little difficult to make the shadowing schemes, but actually it can be done. But the idea here is you grow the 2D of indium arsenide first, and then place some features like the nanowires in situ. So you don't break the vacuum, but you can bring another sample onto the 2D and then just rub it. For example, you can rub nanowires on top of that, and then you can deposit superconductors in situ, and by sonication, you can remove the nanowires. So this is an example. So you can rub indium antimonide nanowires on top of the 2D after the growth, and deposit aluminum on top of everything. And then you will have aluminum like here, and then that's on top of the indium arsenide 2D.
Joon, sorry, a quick question. So this, you grow this in-gas indium arsenide in-gas heterostructure in the MBE system, right?
Yes.
And then how do you physically put a nanowire on top?
So it's like you have two holders. So this is for the in-gas growth, and this is a holder with indium antimonide nanowire samples. It's grown already from outside, and then you just transfer it into the chamber and flip the nanowire substrate and just put it on top of the 2D after growth. And by doing some rubbing and remove the holder, then you can have nanowires on top.
I see. Okay.
And yeah, from this scheme, we also saw very clean and stronger induced superconductivity. And these are archive papers based on this scheme. Okay, let me move on to the third one, selective area growth of nanowires. So this is a little different scheme. So you fabricate before the growth and then grow nanowires. So if you have fabrication of indium silicon oxide mask, and then you can put the sample with the mask into the chamber and grow the indium arsenide. This can be done by MBE, chemical epitaxy, MOCVD, and MOVPE as well. And this is just a way of fabricating the mask. So you put for example, indium phosphide substrate, put oxide layer. This is for the selective etching. And then basically you do the e-beam lithography to make the junctions, and then that's it. So it's not so complicated. You just make the e-beam lithography to make the junctions, and grow indium arsenide or indium antimonide in the MBE system. And then you can play with the temperature and the flux. So if the temperature is too high, and indium arsenide doesn't grow. But if it's too low, indium arsenide may grow, but you will have parasitic growth on the mask. So you need to have right temperature and right flux to have good selectivity. And we find these lines using the read. So when there's when nothing is grown, read is just nothing. And then when the temperature is too low, we see the parasitic growth, then we see polycrystalline ring. So we know something is grown on the mask. And at the right conditions, we see some read patterns on substrate. And if everything is right, then you can grow indium arsenide nanowires. And these have facets in certain directions. And this is example of nanowire in 100 direction. You can see the facets of the indium arsenide nanowires, and interface between indium phosphide and indium arsenide was clean. But this is good, but I mean, this is good for selectivity. I mean, sorry, for the scalability. But the issue is the mobility of these wires are not very large. And as you can see, these are lower than the single indium antimonide or indium arsenide nanowires. And the reason is it's grown on a substrate, so you have defects at the interface. So the lattice mismatch between indium phosphide and indium arsenide is giving the misfit dislocations. And also indium phosphide surface can be damaged from fabrication. And depending on the direction of the nanowires, you may have stacking faults in the middle of the wires. So like these lines, stacking faults in the middle of the wires. So all these degrade the electron mobility of the selective area growth nanowires. So then we were thinking of improving the material system, I mean the mobility of the system, to keep the buffer layer between indium arsenide and indium phosphide, because of lattice mismatch, we saw lots of mismatch locations. And buffer layer can be indium. So we're here between indium phosphide and indium arsenide, and this line is indium aluminum arsenide line. So by having the indium aluminum arsenide buffer layer, indium gallium arsenide or indium aluminum arsenide, by having this indium gallium arsenide buffer layer, we can reduce the lattice mismatch between the indium phosphide and indium arsenide. But the issue is growth of indium arsenide. I mean the right range for indium arsenide and right range for gallium arsenide is different. As you can see, the good selectivity regime is below 500 C, but here when the flux is low, for gallium arsenide, you should have larger than 500. So these two are not matching. So it's not easy to grow indium gallium arsenide, but by introducing atomic hydrogen in the middle of, during the growth of gallium arsenide, we can widen the good selectivity regime of gallium arsenide. So then we can find some area growth window to grow indium gallium arsenide. So by doing that, we were able to grow indium gallium arsenide buffer, and also we were able to grow the capping layer of indium gallium arsenide. So hopefully we have higher mobility by having the buffer and the capping. And the ongoing transport measurement is we're doing that right now. So these selective air growth materials can be used for superconductor-semiconductor devices. You can just grow aluminum on top after the growth of the indium arsenide tag wires. So you can make junctions, islands, or 3-terminal devices. Also, you can have double wires to make other interesting devices. So this can be used. But then I talked about the shadowing scheme for 1D nanowires and also for the 2DAG materials. And for the selective air growth wires, we can also do the shadowing. And this can be done by having the shadow wall structures. So this is before the MB growth, you fabricate the wall structure and then grow the wire in MB system. And you can grow superconductor by having some angle. So from this angle, aluminum is coming. So you can have aluminum only on some certain areas of the nanowire, and you can have junctions or islands. So you can make superconducting islands, and this can be extended to a contact pad, or make a SNS junction, or having a island, but this is disconnected. So you can make many different kinds of devices by this shadowing scheme. And also you can do tin or other superconductors. If you have just some angle for deposition of the superconductor, then you can make these junctions and islands. And this is an example of a SNS junction of indium arsenide and tin. And so this is just a gated junction, and that has been studied. So like other materials, initially the shadowing scheme was not studied, but it's easy to grow aluminum, the blanket aluminum everywhere. So that has been done on top of indium arsenide, indium antimonide, but recently you can use the shadowing scheme to make clean junctions. So this is a summary of what I have talked about. So for single nanowires, and for 2DAX and selective growth materials, the trend is people have used epitaxial superconductors, and then people implemented the shattering schemes to make the clean junctions and devices. That's the trend of this field of study. Okay, that was the part one of my study. And then I have, maybe can spend like 5-10 minutes for the part two. So I talked about tin that has been used after aluminum. And there are some questions about the tin because tin has two structural phases. So this is about the controlling the tin phases. So tin has mainly alpha tin and beta tin phases. Alpha tin phase has cubic diamond structure and is topological. It has topological phases, but beta tin is superconducting phase, and this is about 3.7 Kelvin for bulk. So this is a very interesting material. You can use alpha tin for make like if you have this is topological material. So if you have the alpha tin and superconductor on top of that, then you may use this material system for topological superconductivity. And also you can use the superconducting tin with semiconductors. Then you can use this material for topological superconductivity. So tin is very interesting material for me. And people have studied topological tin. So this is an example that has been shown in 2013. And by doing RPS, people saw the dracons of alpha tin. And this is what I showed earlier. We grew tin on top of indium antimonide and was superconducting, and we saw interesting superconducting features. But then you may ask a question. We grew tin on top of indium antimonide. This is indium antimonide as well. But this paper shows alpha tin, and this paper shows beta tin on the same material. Then why is it different? That's the big question. And that's the motivation I study tin. So to grow tin, it's not trivial. You need to cool down the substrate. And if you do not cool down, then the surface is rough because tin atoms have high mobility at room temperature. They move very fast. They merge each other, they grow as islands. So I need to cool down using liquid nitrogen. So this is liquid nitrogen line. It goes into this part. And this top copper plate is connected to the liquid nitrogen line. It is cold, and that goes into the manipulator, and it touches the back of the substrate. I mean, substrate holder. So that's how I cool down the substrate. And then after the growth, I move the substrate into a small low lock chamber, and then I give oxygen. And oxygen makes the top tin layer as tin oxide, and it stops the moving of the tin atoms. And this is an example of tin grown at room temperature, and it's quite rough. And if you cool down, it becomes smoother. But the interesting thing is that this is on gallium antimonide substrate. If you do not cool down tin, I mean the substrate while growing the tin, I saw beta tin 2-0 phase. So it's basically beta tin 1-10 phase. This is 2-0. Then there is another 4-0 peak as well from XRD. And then as I cool down, if it's in the not very cold, but some cold substrate, then I saw alpha tin peak as well. And then if it's really cold, maybe below 150 Kelvin, then a beta tin 002 phase is seen. So the phase of tin can change as you cool down. It's a little tricky to grow the tin, but if you know your temperature and the control of that, then you can grow different phases of tin on the same set of substrate. And then the second study I did was lattice constant variation. So the first one was on gallium antimonide. But if you look at the lattice constant of the tetragonal beta tin is 5.82. And alpha tin is diamond cubic structure. It has 6.49 angstrom. So then maybe you can think like if your lattice constant is close to beta tin, you may grow beta tin films. But if the lattice constant is close to alpha tin, maybe you will have alpha tin. So that's our hypothesis. And then we vary the substrate lattice constant by having indium, aluminum, antimonide buffer layer. So we can change from 6.1 from gallium antimonide and then 6.48 of gallium indium antimonide. And this is what we get. So we change the lattice constant of the buffer layer from 6.1 to 6.48, which is indium antimonide. And so here, this peak, the dotted red line is showing the peak position of the buffer layer. So we are changing the buffer layer. And then interesting thing is that here you see the peaks of the alpha tin. And they're moving to the left-hand side. That means these alpha tin layer is strained. And then near the gallium antimonide 6.1, we saw beta tin. So this is beta tin peak. And I mean, at higher lattice constant, you don't see the beta tin, right? The beta tin grows when the lattice constant is close to gallium antimonide or indium arsenide. And as you go close to indium antimonide, you see the alpha tin peaks. So from 6.48 to 6.4, we see strained alpha tin. And near 6.1, we saw relaxed beta tin. And in the middle, we saw some relaxed alpha tin as well. So this, the black line is the bulk tin, alpha tin position, and we saw the peak of the relaxed alpha tin as well. And these strained and relaxed peaks are confirmed by the RSM, the reciprocal space mapping measurements. So here you see the gallium antimonide peaks here, and then these the lower parts is from the indium aluminum antimonide buffer layer, and then you see alpha tin peak next to it. This is this area. You see the buffer layer and the alpha tin, and as you can see, they are in the same x-axis. It means they're strained. The strained alpha tin here, strained alpha tin, and strained alpha tin. It's hard to see, but there's a small peak. So this area is confirmed to have the strained alpha tin. And then this area has beta tin peaks from here. And also we saw the beta tin peak here. And these are the buffer layers and gallium antimonide. And beta tin position is different from the gallium antimonide or the buffer. So it's relaxed beta tin. So the RSM is confirming that we see the strained alpha tin and relaxed alpha tin. So the idea here is by changing the lattice constant, you can change the phase of the tin. And we did some transport, and strained alpha tin showed quantum oscillations. So they may show the signatures of the topological phases. We are still studying these oscillations. And also from the relaxed beta tin, we saw the superconductivity that goes to 0. So this is superconducting beta tin. Okay, that's what I have. So the first summary, the advances in epitaxy and shadowing in the superconductor-semiconductor nanowire systems led to enhanced superconducting features. And I talked about the two scalable platforms of 2DAC systems and selective area growth nanowire systems. And also we were able to do shadowing and also the epitaxial superconductor depositions. And tin has been an interesting material, so I studied tin, and I showed manipulating the tin phases by cooling variation and also buffer layer that is constant variation. So for the semiconductor systems, I'm still working on it, but I showed some data from the work I did at the University of Santa Barbara as a postdoc. And this is my current group with students and visiting scholars. We study superconductor semiconductor systems, and also we have interest in topological materials. So we study business antimony and tin and so on. And this is the two-chamber system I have. So I grew 35 semiconductors here and move the sample into the second chamber for superconductors in situ. And I use this system for the semi systems and also team. Okay, thank you very much.
Thank you, Junsu. Does anyone have any questions? Any questions from online?
Can I ask a question from Zoom?
Sure.
So, Junsu, in Europe, I mean, you spelled out quite nicely the problems, materials problems that need to be overcome in order to meet the conditions, right, for observing the Majораnas. In your opinion, which of these different approaches that you've described have the best chance of getting us to a large enough gap and low enough disorder, right?
Well, in my opinion, 2DEC is quite promising. 2DEC system has high mobility, and you can also couple superconductor on top, and it's scalable. So it's good. Well, and
but even if even if we
yes.
forget the scalable part, right now, the field hasn't even proven that there is a single Majorana, right? So I'm just talking about getting rigorous, definitive proof of a single Majorana, I mean, a particle, the qubit. So, what do you think? Which of these materials advances do you think? Do you think it's the 2DEC that because that gives you the high enough mobility and low enough disorder?
Yeah. For now, 2DEC shows the largest mobility, so that's why I say 2DEC maybe. But still, it seems like the theory people is not satisfied with the mobility of the 2DEC, and there may be another advance of the material or device systems from 2DEC.
So even after you pattern your 2DEC, right? What is the highest mobility you get with the?
You can get like 50K or 100K.
So it's still only about 100,000, and these are then field effect mobilities you're measuring.
Because you field effect, or you can make whole bars and to top
you can make whole bars also. I see. Okay.
Yes.
So, just a very nice talk. So I was wondering, because I've been hearing lead telluride is something that a lot of people have started to look at.
Yes.
This, from the nanowire perspective, this seems to be a really good material.
Yes.
What about from a 2D perspective? Can it be grown into thin films, and how does that compare to, InGaAs or indium arsenide or indium antimony arsenide and so on?
Yeah, people grow that telluride by single nanowires, also selective nanowires, and yeah, I see some comparable mobility with the nanowires. I mean, nanowires of indium arsenide, so that's a good thing for that telluride. And you're asking about the 2D thin film of that telluride.
Could it be grown into?
That can be grown.
Yeah,
that can be grown. But the question is, if you just grow the thin film, then what's the advantage of having that? If you can form, quantum well of that telluride, for example, then you can have like barriers, so you can have higher mobility. But that is questionable whether you can do it or not.
But lead telluride, MBE grown lead telluride, I remember many years ago, they got mobilities of like 2 million or so.
Oh, okay, then maybe I missed it.
I'm pretty sure. I should check.
Okay, then that may be a good direction to study. You can form high mobility lead telluride thin film, and if you can couple the superconductor on top, and that may be an interesting material system.
So if I could ask another question, because it seems like the field spend a lot of effort in trying to make shadow evaporation of shadow, right? But
yes.
one cannot just brute force lithography pattern whatever you want and deposit. Why do you have to use this shadow?
Oh, you can do that. You can just pattern and evaporate superconductors, but then you may have some disorder from the fabrication or oxide layer at the interface, and that degrades the signals you get.
So that hasn't been figured out how not to have that in the lithography process.
Well, people have studied a lot. So, for example, I showed earlier, maybe, yeah, sorry. I talked about studying, improving the signals initially. So here. But using algomilling was really bad. People try to make the surface passivation to make the interface clean.
Yeah.
And it was not enough to get stronger signals. So, and then people used epitaxy superconductor, and it was the best. So from the demonstration of these things, and people tend to go to the epitaxy superconductors.
But then the downside is you're, covering up the entire surface. Then you have to now think about how to remove the aluminum, right? Or have
That's right.
clever mask of not depositing it, right? Which is not as easy as just, using lithography to
that's true.
whatever structure you want to, right?
Right, it's a little trickier.
Transferring nanowire on top looks like art, right?
Yeah.
It's probably, it's like, Van der Waals stacking, right? It's students manipulating things and touch and that kind of stuff, right? Isn't quite industrial scaling kind of approaches.
Yeah,
Not yet.
that's true. Not yet,
Right.
yes.
Right. Thanks.
Jun-Soo, for your talk today, and thank you everyone for your attention.
Thank you.
Thanks, Joon-Soo. Nice talk.
Yeah, thanks a lot. I wish I'm there to give a talk. But it's also good to do the webinar.
Yeah, well, since you've described this nice growth of tin, we should talk from the, if you want to send another student for RSVP, since we now have tin in the chamber, it would be interesting to do RPS measurements of, so the only problem is that we can't, of course, tune the substrate buffer layers and all that easily. You're using 3.5s, right? So